So we can now move to project 11, multi-scale and statistical analysis of observed and simulated astrophysical data.
Yes, 1 second. Let me just find.
Can you see the screen?
Yeah, I can see the screen. Okay, so welcome. We're group 11, and you can see on the screen the participants and supervisors. And so next slide. So first of all, what are we doing and why are we doing it? So as we've heard in the past 2 weeks, the ISM has structures on all scales from the galactic all the way to, you get dense filaments and all the way down to dense cores. And power spectra can show us the structure in the ISM, and through that we can study all the features, gravity, turbulence, magnetism, all of that stuff. And the power spectrum comes from the Fourier transformation of the image. So we see on the left Herschel's fire image of GT08 in Orion, and on the right we can see the same image in Fourier space. And then in the center we see the one-dimensional power spectrum. So our goal for the past 2 weeks has been first to learn about the programs that can help us study power spectra, and then fit these programs to observations and simulations. So next slide, yes. So the program was use a Jupyter Notebook tutorial on Google Colab, and we've listed the programs. Our main programs used were Turbustat, PyWavelet, and Astrodendro. And then, of course, we use the basic Python astronomical packages. Next slide. So yeah, we used these programs on 2 different observations. One of them was Polaris and the other was Perseus. So Polaris is a high latitude nearby quiescent cloud. It has no active star formation. It only has prestellar cores. Meanwhile, Perseus is a bit further away. It is active. There's signs of star formation, including class 0 protostars. Yes, and next slide.
Hi, I'm Mathilde. I'm gonna present you the results we get when applying all the different methods we see during the first week on the 2 field Emma just show you. So first, the power spectrum apply on Polaris and Perseus. As you can see, they are following nice power law, and the slope of this power spectrum can help us to understand how gravity and turbulence shapes the molecular cloud and the physical condition within those clouds. Then we perform the wavelet decomposition of the maps, which can help us to understand at fixed scale from where the power is originating coming from. So from at large scale, middle scale, or small scale. Next slide, please. Then we look at the probability density function of the column density maps. And as you can see, for example, here for the Polaris PDF, it is almost following a log normal law. However, as you can see, there is some extra power, a tail of extra power, and this is a characteristic of un-Gaussianity within the fields, which could not be seen by only looking at the power spectrum. For example, if you simulate from the same random amplitude a Gaussian field and a non-Gaussian field, they would have the same power spectrum. However, they will have totally different PDF. And this extra power actually helps you to understand the star formation within the molecular clouds. So that's our results for the first week. Next slide, please.
Okay, so I'm Alvaro, and I'll start explaining what we did in the second week. So we wanted to simulate a patch of turbulent gas using RAMSES and Osyris to sort of like read in the outputs of RAMSES. So RAMSES is a code developed by Romain Tessier, and you have this n-body part tracing dark matter and star particles, and then the mesh or the grid that traces the hydrodynamics of the gas. And you have multiple features included in RAMSES, of which we were interested in the turbulence prescription. So we actually have, an observation, in this case Polaris, and we wanted to sort of simulate a patch of turbulent gas with RAMSES to see if we could compare and apply and get the same statistical tools and get similar results. Yep, so this is the evolution of a turbulent box. So we start with output number 1. This is this like green patch on the top of the slide. And you can see that there's like a vertical line showing the PDF at a certain density. And as we press play and we let the simulation run, we obtain what we have in output 14 in red, this more broadened PDF distribution that is more or less settled. And this sort of settling or stabilization of the simulation can be seen in the right-hand side plot, bottom right. So we can relate the width of the distribution to the RMS velocity of the gas. So in yellow triangles, you will see the RMS velocity of the data, and in green, we see the fitted broadening of the PDFs using some turbulent model to get our RMS velocity. And it's more or less consistent, but we have a bit of weird things going on in the final outputs due to the shapes of the PDFs.
Okay, yeah, so instead of analyzing the 3D data, we can also project these to obtain 2D data sets again, which we can analyze using the same tools as the observational data. So what you see here is the simulation of the turbulence again with different resolution, and yeah, this is always the projected 2D surface density. And yeah, we can apply the same tools as I said. So on the top you see the Fourier power spectrum, and again the wavelet decomposition very closely resembles the Fourier power spectrum. What is important to notice is that with higher resolution, we can also sample the smaller scales here, which are at higher wave numbers. The second tool we used here is the PDF, and what you can see, especially at a high resolution, is that the simulated PDF very closely resembles a log normal distribution you see here at the orange fit, which is what we would also expect for the pure turbulence that we simulated. So yeah, just to conclude what we did, we used different open source tools to perform multi-scale and statistical analysis. And all of these tools are complementary. So you can use the power spectra to analyze the Gaussian fluctuations at different scales, or analyze the global average via the PDF. Finally, also the non-Gaussianities can be analyzed using the wavelet decomposition. We applied these tools both to observations and simulations and compared these, and thus were able to constrain different physical aspects such as turbulence or self-gravity. So yeah, with that, we want to thank for your attention and feel free to ask questions.
Thank you. So just a small note, I mean, I have a technical problem, so I can't see anymore my screen, but as long as you can do it, we can go on. So there is a question on the chat. So there is no access on the PDF for the simulations?
No, not for the simulations in this case, because yeah, we also didn't include gravity in these, so that means it's really pure turbulence.
Okay, thank you.